So back to the actual written part. Okay, so we end up, we're going to let angle PON. Okay, remember PON. So that's theta. So we're going to let angle PON be theta. And we'll find a theta here. There we go. So if that is true, then we also know sine theta equals, well, let's talk about this. When we talk about sine and cos, we're thinking SOHCAHTOA. So we know that sine theta is opposite over hypotenuse. So let's put that opposite over hypotenuse. But if I look at my unit circle here, if I do opposite of theta is y, and the hypotenuse is here, which is 1, because that was the radius. Now, you would never leave y over 1. That would reduce to y. Now, whether you realize it or not, that's pretty important. And we'll talk about it in a second. Let's do the same thing for cos. Now, although I'm doing it for sine and cos, tan also is related to this as well. But we usually just talk about sine and cos at the moment. So we know that cos theta equals adjacent over hypotenuse. And again, if I look at my unit circle, and sorry, that looks so messy, my unit circle, adjacent here would be the x, and again, the hypotenuse is 1. And just like for the sine, we would put that as being just x. Now, as I said, this is really important, and some of you maybe recognize it as being important, but just to point out exactly why it's so important, I'm going to block out part of our work. Properties, let's just turn it all black. So let's look. If you notice, we have sine theta equals y. So if I take out the inner part, you can see that sine theta equals y. And similarly, if I move this down here, I end up with cos theta equals x. So in a sense, we have defined both sine and cosine in terms of a coordinate system, where cos theta is x and sine theta is y. So we're going to delete that. So this is very, very important. So it's going to have stars. It's going to follow us for the rest of this unit as well as into the next unit. So it is very important. So what we end up putting here is, oops, therefore, sine theta equals y, and cos theta equals x. All right, so we have redefined it, but at the same time, we still have an acute angle. So if you notice, when I said our note is on obtuse angles, and now I've proved something when it comes to acute. Now the reason we do that is something that we do know, And what we're going to do now is I'm going to take that P and I'm going to rotate it so that it ends up being in the second quadrant. So that's the second part of our note. So continuing, we would now rotate the P so that it is in the second quadrant. So what we end up having when we do that, and again, I'll just draw, this time I'm not going to do a full-blown rip the thing apart. So here's my axes. I'll go over here and get my unit circle again. And I guess it would help if I made my axis straight. There we go. So here's my unit circle. And if it was put here and... Okay, that's better. Now we can see what's going on. So all we're doing now is we are putting point P over in the second quadrant somewhere. Okay, and again, because we defined up here what the angle is, and the angle still would be PON, what we end up with is our theta becomes this, okay? But our coordinate still is XY because we defined that, we calculated that when we did the unit circle. So everything else works out the same. Now, what does that mean? Well, let's take a look at this a little bit closer as well. And I realize that today there's an awful lot of talking because how important this section is. So what happens, think about this, when you have an angle in the first quadrant, what can you tell me about the coordinates for x? Well, the coordinates for x in the first quadrant are all positive. And the same thing is true in the first quadrant for the y's. So the y's are all positive. So that means that any angle that's between 0 and 90, for both sine or cosine, the ratio should come out as a positive number. And if you take your calculator and you do the cos of 89, it will come out as a positive number. If you take the sine of 1 degree, it comes out as a positive number. And that's because both the x and y values in the first quadrant are positive. However, if I choose an angle greater than 90, it's different over here because in the second quadrant, my x is no longer positive. My x has negative values. So that, and remember our x is cos, so it means if I took my calculator and took the cos of 105, the ratio that I would be getting would be a negative number. And that makes sense if I define it based on this coordinate system. So your calculator already knew it has to be negative. However, if I look at values for sine in the second quadrant, such as 100, sine of 100, what I end up with is also a positive number. So, and the reason being again is because y is positive in the second quadrant. So, one more thing that we will write down on here to keep us going is, again, related to our angle. So, angle POA, okay, and that was based on this being O, and here is still our A that we had defined from the first unit circle. Is obtuse, and we define the coordinates of P as cos theta sine theta. Okay, so there is our ordered pair. Our ordered pair coordinates of P are cos theta sine theta. Now, as I said too, the same thing will happen for tan theta. So we'll just add that to this part of the note so that we have that. And I know you're getting sick of me talking because it's a little more than 25 minutes so far, but that's all right. Since I can't be there, I don't want you to miss me too much. So if I look at tan theta, tan theta, as you already know, is opposite over adjacent. I mean, that's how it's defined. So when I think about that and I go back up to this unit circle, opposite over adjacent. So opposite is y, adjacent is x. So what we end up with, and we'll continue this, is that means that tan of our theta also equals y over x Now, furthermore, you know what y equals and what x equals because we've already defined that. We defined that the x is cos and that the y is sine. So really, even further, we can say that tan theta equals sine theta over cos theta. And this is special in the sense that it has a special name, this relationship, tan theta equals sine theta over cos theta. It's actually called the quotient identity. And later on in this unit, we'll be using the quotient identity to when we're doing trigonometric proofs. So it's something that we use to prove other things. All right, so continuing, so we've done this, we've redefined things, but what does that actually mean to us? And that can be a little bit, it's going to be a little bit harder in a sense. So what I'm going to suggest before I go any further, if you need to stop now and rewind in order to get the note down, because it's important to have these pictures because we do make references to them as this unit goes on so that you can then look back at it. I will make reference to it as well in future notes because it's, as I said, it's fairly significant because we have redefined things. Okay, so pause now and then after you can just keep on going.